Okay, good afternoon. Why don't we get started? At the end of the last lecture, I forgot to mention how a white LED is achieved. So I actually brought a white LED today so you can take a look. But basically, if you look at this LED, it's, you should see that it's yellow. And then when you push the button, it looks white. So basically what it is a blue LED, and it's coated with yellow phosphor. So phosphor is just a material that can absorb light and re-emit it at a lower energy, so a longer wavelength. So yellow and blue together looks like white to our eyes. So that's how a white LED is used, and that's used in a lot of little compact flashlights nowadays. Okay, so I wanted to answer some of the questions, good questions that were asked last lecture. So first one was, why are the contacts to the back side of the solar cell made only at certain points rather than across, let's say, the entire back surface? So we're talking about this structure here on slide 12. Why? We know we need to have heavily doped silicon in order to have a nice ohmic contact to the metal conductor on the backside, aluminum. But why is this heavily doped? Why is contact only locally made like at points, and you only need the heavily doped material right at the contact points? So why is that the case? So one student did point out that, and it is indicated in the PRA textbook, that this backside, a combination of an oxide and aluminum together serves as a good mirror, a reflector for light to reflect back into the silicon. So the solar light that enters into the cell, some of it has a very long absorption distance. So the longer the wavelength, the longer it takes on average for the photon to be absorbed by an electron to create an electron-hole pair. So the longer wavelength photons can easily reach the backside of a silicon solar cell if it's not too thick. Now, typical single crystalline solar cells are about 100 or 200 microns thick. So for the longest wavelengths, on the average, you can reach the backside. And so basically, you want to trap the light so that it bounces around inside the cell and eventually will create an electron-hole pair. So this oxidized silicon backside and aluminum coating serve to reflect back the photons so you can trap light at the backside. So just like the front was textured to allow maximum absorption of light, the backside is shiny to reflect light back, to trap light within the cell to increase in efficiency. But you might ask, well, why not just increase the area of these P+ regions? Why do they have to be really small, like point contacts? So it turns out that this kind of a structure is only used in advanced, more expensive solar cell designs. So let me go back to the answer here. Okay, so there is that the first part, one part of the answer is that you really want to have oxide and aluminum on the backside to trap light efficiently. But in the late 1980s or so, researchers found that if an electron-hole pair is generated within the silicon, the minority carriers can recombine easily if there's a heavily doped region in the contact region. So basically, if you have a lot of heavily doped P+ silicon at the backside of the solar cell, it's very likely that there are defects there associated with the doping process. You can actually have carriers recombine before they are collected by the depletion region. So another reason why you try to make contacts only at certain points, not along the entire backside, is so that the generated carriers will have a higher probability of diffusing to the depletion region before they recombine. Because if they are generated near the backside, they could easily get trapped and recombine non-radiatively. In other words, they can emit photons, but not in the visible light. They will not be collected by the depletion region to generate electricity. Okay, so it's a two-part answer. So bottom line is to increase the energy conversion efficiency. In other words, as the ratio of electric energy or electric power you get divided by the total solar power illuminating the solar cell. We want to maximize that ratio. Okay, another question that was asked is what limits the lifetime of an LED? So it turns out, I don't know if any of you remember a light bulb, a conventional light bulb. It's like a little tungsten filament in there that you run current through, it heats up and it glows. Okay, it's black body radiation. So a conventional light bulb will have a limited lifetime because that filament can break. I mean, over time, it'll get stressed, and it'll break, and the light bulb fails to work. A light-emitting diode actually doesn't truly fail. The LED lifetime is defined to be the amount of time it takes when the LED is on before the light output reduces like to be 70% of the original light output. So basically an LED usually won't just fail and stop turning on. Basically it'll still continue to function, it's just not going to be as bright as before. And so that's typically up to 100,000 hours, and it depends on the temperature at which you operate it. Okay, so why does the light output of an LED degrade? It's all fundamentally related to the fact that it heats up when it's on. So you have current flowing through the LED. So does anybody remember roughly how much current is flowing through this LED that I'm passing around? Order of magnitude? It's like milliamps, right? Oh, and it's not even the highest brightness, right? I actually limit it to milliamps so you don't blind yourself. Okay, so let's say a nice bright LED would operate at like 10 milliamps on that order. And how small, how many square centimeters is the chip? Can you tell? It's like about a millimeter on a side. Yeah, it's pretty small. So the current density is maybe, let's see, there's no pen. Okay, so current density would be, let's say, 10 milliamps flowing in 0.01 square centimeters. So that's, what is that? That's 1 amp per centimeter squared, something like that. And the typical volt is a few volts, 2 or 3 volts that you need to apply across the LED. So if you run it at a very bright, high level of brightness, then you can exceed 1 watt per centimeter squared of power dissipation. Just as a reference, 10 watts per centimeter squared is in the range of an electric stovetop. Okay, so how many of you are familiar with an electric stovetop, like the ceramic stovetops? Basically, you're just running current through a coil, and it's heating up. So basically, fundamentally, the LED can heat up if it's very bright. And when you heat up the LED, a lot of different things can happen. So first of all, the packaging, that plastic package, it's epoxy. That material is picked for a good reason. It has a higher index of refraction than air, and so that helps to reduce the amount of internal reflection of light, so it allows more light to escape from the semiconductor diode. So that epoxy material, if it heats up, like any organic material, will age, and it can turn yellow, so it can actually become less transparent. So then that can kind of block some of the light coming out. That's what happens when the epoxy package heats up. If you heat up the diode, there's a difference in coefficient of expansion, thermal coefficient of expansion, between the metal wire and the chip, and that can actually weaken the physical wire bond. So that could cause failure, or at least increase the contact resistance over time, so you don't get as much current flowing through the LED. And then fundamentally inside the semiconductor itself, when we grow these materials, these are pretty exotic compound semiconductor materials here, the 3,5 materials. And oftentimes it's impossible, it's not really practical to grow them with 0 crystalline defects. So there might be a crystalline defect in the diode, and as you heat it up over time, those defects, atoms in the semiconductor, if you heat it up, will be more mobile, and over time they can actually grow the defects. So it's kind of like example is like a crack in a semiconductor. If you put stress on it, thermal stress on it, and increase the mobility of the atoms, you can actually cause a crack to propagate, to grow. So it's like that. The defects can grow over time as you heat it up due to thermal stress or just simple thermal diffusion. And so rather than having direct recombination of an electron going from the conduction band into the valence band, you have these defects that provide that have associated allowed energy states in the band gap. So rather than recombining like this, you can actually have an electron going like this, and then a hole coming up, which is the same as an electron falling down. Right? So basically then you're not going to emit light in the visible spectrum. So that's what can happen over time, but fundamentally it's all due to thermally induced, heating induced stress. Okay? Any questions regarding optoelectronic devices, diodes, solar cells? I think I didn't, I know in the beginning of the class people has indicated some interest in solar cells. So I should mention what we cover here is like a single crystalline solar cell. So like I said, starting with a silicon wafer, hundreds of microns thick. But for lower cost, okay, so those, let me just mention. So those are the kinds of, like these kinds of solar cells. These are single crystalline silicon when you look at a solar cell, okay? But for lower cost, it's easier to make solar cells on large pieces of glass, large area to collect more electricity. And those are fabricated in a different manner. You start with a piece of glass and you can coat the glass with a thin film, like a micron thick silicon. But that silicon layer is not a single crystal, okay? Because when you deposit silicon like at one part of the glass and another part, there's no way you're going to be able to guarantee that the atoms are aligned perfectly, across with a perfect atomic lattice. So you have a lot of crystalline defects in a thin film solar cell. So the trade-off is, okay, in engineering there's always a trade-off. You have lower cost for thin film solar cells, lower cost per area, but what do you think the trade-off would be? Lower efficiency, that's right, because for the same reason, you have, basically, when you generate electron hole pairs, they can recombine before reaching the depletion region because of those crystalline defects throughout the thin film. Okay, so the efficiency of a thin film solar cell is usually well below 20%, and the energy conversion efficiency for a single crystalline solar cell is usually now above 25%. Okay, so you have a trade-off there. Okay, I think that's it. So let's move on to the new topic then, MOS capacitor. So we've covered PN junctions, those are inherent in a MOS transistor. And the heart of a MOS transistor is the MOS capacitor. So we'll have to spend a few lectures on the basics of MOS capacitors. So today we're just going to cover the energy band diagrams. Okay, how to draw them. So just a brief introduction. So MOS stands for metal oxide semiconductor. And so the structure on a cross-sectional view looks like this. We have nominally a metallic gate electrode. Metallic just means it's very electrically conductive. It behaves as a metal rather than a semiconductor. So we have an electrode that is patterned over an insulating film of oxide. Okay, so this is the oxide. Then you have the stack over the semiconductor. So that's why it's MOS capacitor. Okay, so we usually apply a voltage in an integrated circuit, a voltage between the gate. There's a circuit which applies a voltage difference between the gate and the semiconductor. So for now, for most of the discussions in the next few lectures, we'll assume that we'll use the semiconductor, the backside of the semiconductor, as a reference in terms of electric potential. So we'll just say that the back of the semiconductor is ground, at ground potential. Okay, so electric potential there's no absolute measure, it's all relative. So we'll just say, we'll talk about potentials relative to the backside of the semiconductor. Okay, so in the most advanced integrated circuits today, we actually do use a metallic material for the gate. But for a few decades, for about more than 3 decades, the most for at least 2 decades, the most common gate material used in integrated circuits using MOSFETs was heavily doped silicon. Okay? So it's heavily doped, so it's degenerately doped. It's doped typically close to 10 to the 20 per centimeter cube. And this thin film of polycrystalline silicon, it could be anywhere from 1/10 of a micron thick to a micron thick. Okay, so this thickness is typically 0.1 to 1 micron thick. This semiconductor film is doped, it is deposited and doped, depends on the fabrication process, very heavily. And because it's deposited on oxide, silicon dioxide, so silicon dioxide is the most common dielectric still used in integrated circuits today. The oxide is amorphous. It has no crystalline structure. Okay, it's just amorphous. So if you're depositing a thin film of silicon on top of an amorphous substrate, the silicon atoms, when they come down and hit the surface, they have nothing to line up with. So basically, it ends up to be polycrystalline. Okay, it's not a single crystal. But it doesn't really matter because we're just simply trying to use it as an electrical conductor. We're not trying to use it for its semiconducting properties. So it's not a big deal if the material is not single crystal. Okay, so we dope it to be electrically very conductive. And for N-channel transistors, we actually have it doped heavily N-type. Okay, so that means the work function is about 4.1 electron volts for heavily doped N-type polysilicon. For P-channel transistors, so in a complementary MOS technology, CMOS technology, we have both N-channel and P-channel transistors. Since the late 1980s or so, we had different gate materials used for N-channel and P-channel transistors. So for P-channel transistors, the more preferred gate material is P-type doped polycrystalline silicon. So here then the work function is about 5.2 EV, 5.1 or 5.2 EV, in that range. Okay? All right, so later on we'll talk about why certain work functions are better for certain types of transistors. Okay, so you can sort of assume in all of the energy band diagrams that we draw in this class that the energy band diagram for polycrystalline silicon gate is the same as for single crystalline silicon like semiconductor body. Okay, so sometimes we'll call this the body of the MOS device. Okay, now what about silicon dioxide, that layer? What does the energy band diagram look like? Well, if you remember from maybe the first week of this class, an insulator has a band gap as well, but it has a very large band gap energy. So for silicon dioxide, it's about 9 electron volts. For silicon, it's only 1.12. So what does a large band gap imply in terms of conductivity of a material? Not very electrically conductive, right? And that's because the intrinsic carrier concentration is exponentially dependent on the band gap energy. And if the band gap energy is like 9 times or 8 times larger than silicon, then the intrinsic carrier concentration will be many, many orders of magnitude less than in silicon. So silicon dioxide is one of the best electrical insulators used in integrated circuits today. So not only does the band gap energy different for silicon dioxide compared to silicon, but also the dielectric permittivity. So anybody remember the relative permittivity of silicon? Roughly about 12. Okay, 11.7 or 12. Okay, so this is basically about 1/3 of the relative permittivity of silicon. So we'll use that ratio, this factor of 3, to keep some calculations simpler in this class. Okay, so the dielectric permittivity of silicon dioxide is 3.9. Okay, and then the most common semiconductor used in integrated circuits today, digital integrated circuits, for computing is silicon. Okay? And so today, I think we're going to look at both N-type and P-type silicon. We'll focus on, to explain the fundamental concepts, we'll first focus on P-type, this case of P-type silicon, which is used if you want to form an N-channel MOSFET. Okay, so I have to define one more term, and this is the bulk semiconductor potential, phi sub f. Okay, so this is the body or bulk semiconductor. Okay, so we're going to assume that the semiconductor in the MOS structure is uniformly doped, just to keep things simple. And we want to keep track of where the Fermi level, far away from the oxide interface, where that Fermi level is relative to the intrinsic Fermi level. So basically, the bulk semiconductor potential is illustrated on this figure. It's basically the distance or the difference between the Fermi level and the intrinsic Fermi level, or in other words, EF minus EI divided by Q. Right? So a bulk potential, this is has units of volts. Okay, and on energy band diagram, we're talking about electron volts. So you just put a Q in front. So Q times phi f is just going to be EI minus EF. So for P-type silicon, phi f is greater than 0. And for N-type silicon, phi f is negative. Okay? So this is the definition. So just remember that the larger phi f is, the larger the more heavily doped your silicon is, the larger phi f is. Okay? That's basically it. So the equations are given here. So like starting from the first week, if let's do a quick example. If Na equals 10 to the 18, which is probably in the range that you'll use for your transistor design project. Have to be careful now with the units. So what is phi f in this case? And let's assume the Boltzmann approximation holds. 48, that's right. So it's 0.48 volts. That's good. Okay, so we'll start with the easy case, which you never see in reality, really, which is, okay, now we bring the metal, oxide, and semiconductor materials together. Right, so when we were looking at metal semiconductor junctions, we had to bring two materials together and charges transferred and to reach an equilibrium state. Same thing for p-n junctions. You bring p and n-type materials together, charges transferred, and you reach some equilibrium state. So now we have to do the same thing. We have to look at the energy band diagrams for metal, oxide, and the semiconductor before and after they're brought together. Okay, so in the metal, there's a continuum of allowed energy states near the Fermi level. Okay, and so on average, most of the allowed energy states below the Fermi level are filled, and there are a bunch of allowed energy states right above the Fermi level that are mostly unfilled. Okay? In the oxide, we just have a large band gap energy here. Okay, so this is around 9 eV for silicon dioxide. And then in silicon, this is a p-type material, so the Fermi level is above mid-gap. And just to remind you, the work function of silicon is defined to be E naught minus EF. Okay, and electron affinity is shown here, so that's 4.05 electron volts. Okay, so hopefully these energy band diagrams look familiar, except for the oxide, which is new. So now we insert an oxide in between the metal and the semiconductor and bring them together. And if the work function of the metal and the semiconductor are exactly the same, then you naturally automatically get the Fermi levels lined up so that in equilibrium, you basically just have a very simple energy band diagram like this. So some numbers to keep in mind. Let's see, did I bring my notes? So this distance here for the silicon dioxide interface, that potential barrier for electrons to flow into the oxide is 3.1 electron volts. So in all of your energy band diagrams, you should be drawing, if I ask you to indicate that electron potential barrier height, it's 3.1 electron volts. So can somebody tell me then what is the potential barrier for holes to enter? Holes are in the valence band. So what is the potential barrier for holes to enter into the oxide then? Just roughly. It's about 4.8 electron volts, right? Because we know that the band gap energy of silicon is 1.12 eV, and we know the band gap energy of oxide is 9 eV. Okay, but in reality, this is usually never the case. So let's look at the general case then. Different work function. So because, so this might be a little bit confusing, but as I mentioned, in a circuit, there's always some conductive path, electrically conductive path, between the gate and the semiconductor. So carriers will still want to go from one side of this system to the other due to a difference in work function. So in this case, they don't flow through the oxide because there's a potential barrier. They flow through the circuit to actually reach the equilibrium state. So again, we have the energy band diagrams on the left for the three materials before they're brought together. And on the right, we bring them all together. So the key thing, if I ask you to draw the equilibrium energy band diagram, the first thing you should do is draw a straight line across for the Fermi level. Okay? So at equilibrium, the Fermi level has to be constant throughout the system. Then the next thing to do would be to draw the, far away from the oxide, nothing should be changing. It should be sort of like equilibrium conditions. So you can draw the energy band diagrams because you know the dopant concentration. So you know that the Fermi level has to be below the intrinsic level. So if you know the dopant concentration in silicon, you should be able to draw the energy band diagram to the right. Okay, then you just need to be able to, so the other thing, as we sort of introduced when we talked about the energy band diagram for metal semiconductor contact, the free electron energy level has to be continuous throughout the system. Okay, so that means there can't be sudden jumps or jogs in this curve. And also this electron affinity and this electron affinity, these are properties of fundamental properties of these materials. Okay, so those cannot change with distance either. Okay, so bottom line, because the electron affinities for silicon and for silicon dioxide are fundamental properties, they don't change. That means this distance here still has to be 3.1 electron volts. Okay. So that's one thing. And then, so you know that and the same thing over here, this distance here can't change from this distance here is dictated by the properties of the oxide and the Fermi level of the metal. Okay, so basically then you know that there has to be some voltage dropped. Okay, so you start out with a difference in work functions. So you know that when the materials are brought together, charge has to be transferred. Let's see, in this case, is charge moving? Okay, are electrons, okay, so this is a p-type material on the right. So are electrons going to want to be in the p-type material more than in the metal? I mean, which direction are electrons going to want to flow? Looking at this. Okay, so the work function of the silicon is greater than the work function of the metal. Wait. Is that right? Yeah, the work function of the silicon is greater than the work function of the metal. So which direction are electrons going to want to flow? Into the silicon, right? Because they have like lower energy there. Now, this is p-type silicon. So if you add electrons to p-type silicon, they'll end up making the surface less p-type. They'll make the silicon less p-type. So that's actually what happens here. Here's the Fermi level. The edge of the valence band is departing, is getting farther and farther away from the Fermi level. In other words, at the surface, the silicon is becoming less p-type. That's because you've added electrons to that side. Okay, so we know that the energy band bending has to go sort of in this direction. And so there's some voltage dropped across the silicon. There's also going to be some voltage dropped across the oxide. And we'll explain that in the coming slide. But bottom line is you have a difference in work function. So at equilibrium, you have to have some energy band bending to exactly cancel out that difference in work function. So that's what we did for the metal semiconductor contact, and we did that for the p-n junction. Basically, to bring the Fermi levels to the same level, we had to have some band bending. Except now the only difference here is that some of the band bending is occurring in the silicon, and some of it also occurs in the oxide. Okay, so when you had a p-n junction forming, part of the voltage difference, that built-in potential difference, part of it dropped in the p-type silicon and part dropped in the n-type silicon. Here, part of this work function difference is dropping in the oxide, and part is dropping in the silicon. Okay, and you have a discontinuity here in the conduction band edge because silicon dioxide has a larger band gap than silicon. Okay, so the guidelines then for drawing an MOS energy band diagram, and we'll start from scratch again in the next slide. So at equilibrium, Fermi level is flat. Okay, so that's the first thing to remember. Also, it turns out that the Fermi level is flat within the semiconductor always. So it's flat within the semiconductor always. So not only at equilibrium, but we can always assume it's flat, even if we apply a voltage difference between the metal and the semiconductor. And the reason for that is because we have a silicon dioxide. We have an oxide layer that prevents current flow, DC current flow, in this lateral direction here. So we know that no current can flow in this direction. So we can validly draw a constant Fermi level within the semiconductor, even if we're applying a voltage to that semiconductor. Okay. So the energy band bending, how about within the oxide? What's happening in the oxide? For now, we're going to assume that there is no charge density in the oxide because it's an insulator. So we'll assume ideally there's no charge in the oxide. So from Poisson's equation, that the derivative of the electric field with respect to distance is going to be equal to the charge density divided by the permittivity of the material. Well, if the charge density is 0, then the derivative of the electric field is 0. So in other words, the electric field is constant. So remember, the electric field is equal to 1 over q times the slope of the band edge, if I recall correctly. So basically what this means is that the derivative of the band edge is going to be a constant. Yeah, so electric field is constant, so the derivative is constant. So if we go back and look, this is a straight line. The slope is constant. The slope of the energy band diagram is constant in the oxide. Okay, and then finally, and this is not really, it's not easy to draw this last point, but just qualitatively you should know that the dielectric displacement an interface between two different materials should be continuous. Okay, and so that means that the dielectric permittivity of the oxide times the electric field within the oxide has to equal to the dielectric permittivity of the semiconductor times the electric field within the semiconductor at the interface. So right at the interface, the dielectric displacement has to be continuous. In other words, if you go into oxide or silicon, you should have the same dielectric displacement. So that means then that the strength of the electric field in the oxide is going to be about 3 times, because of the ratio of the silicon permittivity to oxide permittivity, it's roughly a factor of 3. The electric field strength in the oxide will be higher than the electric field strength in the silicon at the interface. Okay? So if you were to draw the energy band diagram very precisely, then the steepness, okay, in principle, then this slope here, I'm just going to sketch it with a different color. This slope here should be like 3 times as steep as this slope here, if you were drawing this accurately. Okay? Now, the reason why it's hard to draw it this way is, I should mention. So typical, this X naught, which is the thickness of the insulating layer. So typically, X naught is less than 5 nanometers. And the most advanced technologies today is close to 1 nanometer. Okay? Typically, what is the the depletion region width? Right? If we have this width of the depletion region here, just on the order of magnitude. It could be a micron or 1/10 of a micron. So it's like, let's say, 1/10 of a micron or so, in that order, depending on the dopant concentration. So that's like 100 nanometers. Okay. So in other words, the depletion region width is usually like, it could be 100 times wider than the oxide thickness. Okay. So, but it's just kind of hard to draw that. Okay. So that's why we just draw it here. Okay, so the oxide we know in reality is nowhere comparable thickness as the depletion width. So that's why in a practical drawing, we're not going to show the slope being steeper in the oxide compared to the silicon, but in reality, it should be. Right? So in reality, you should be drawing something steeper and much, much thinner, like this. Right? In reality, it should be more like this if you draw it to scale, and the metal energy band diagram would go up like this. Okay, so if you were trying to draw it more precisely. Okay, whenever you draw MOS energy band diagram, assuming it's silicon dioxide and silicon, you should always note that the barrier height for electrons in the silicon looking into the silicon dioxide is 3.1 eV, and the barrier height for valence band electron holes is 4.8 eV. Okay, so should keep those in mind. And later when we're going to talk about applying a voltage now across the MOS structure. So if we apply a voltage, so it's not in equilibrium anymore, just like in a p-n junction, the difference in the Fermi levels on the left, on the p and n side, that gives you an idea of how much voltage is being applied. Same thing here. You look at the difference in Fermi levels between the semiconductor and the metal, and that will give you the magnitude of the applied voltage. Okay, so it's the applied voltage between the gate and the semiconductor. Right, so remember, so technically this would be VG. This is the voltage difference between the metal and the semiconductor. But remember, we're using the semiconductor as the reference potential. Okay? Does anybody have any questions about these really basic aspects of coming up with the energy band diagram for an MOS structure? Okay, so let's go through the example again. So this is ideally how you would do it. You start, if I ask you to draw an equilibrium energy band diagram, you start with a horizontal line like this for the Fermi level. It's p-type material, so you draw the energy band gap here, 1.1 eV, with the valence band closer to the Fermi level than the conduction band. Okay? Let's see, so what's the next thing that would be good to draw? I guess, okay, so I don't know, what's the next thing that you think would be easiest to draw? Like, do you want to draw the oxide or the semiconductor? Oxide, yeah, that's probably easier, you're right. Okay, so I'm going to draw the oxide sort of in the middle here. Ideally, this should be a vertical line, maybe not. Let's try again. So what I'm drawing here is assuming that the metal is N plus polysilicon. Okay, that's as illustrated on the left. So you have an energy band diagram for this heavily doped polycrystalline silicon. You can just assume, it's not accurate, but the band gap is similar to that of single crystalline silicon. So the Fermi level of heavily doped polysilicon is right at the conduction band edge. Okay, so if it's polycrystalline silicon, then you know this distance, right? What is that? We reviewed it on the previous, or two slides ago. 3.1 eV. Very good. And this distance here is 4.8 eV. So I'm not going to really draw it to scale here. Okay, so then we know qualitatively there must be some voltage drop. So let's just draw that like this. So that's kind of what it's going to look like in the oxide. Now we know that the conduction band edge in the silicon has to be, well, the difference in the conduction band edge, right, this is E sub C in the oxide. So the difference in E sub C in the oxide and E sub C in the silicon is 3.1 eV, right? So whatever this distance is, that has to be the same as this distance, say right here. We know that there must be some band bending in the silicon that looks like this, so that this distance here is 3.1 eV. Okay? Now we know, okay, the band gap energy should be constant throughout the semiconductor, so you can just draw a parallel valence band edge like this. If I drew this kind of accurately, then the slope here at the edge, at the oxide interface, is going to be less than the slope in the oxide here, right? The electric field is stronger in the oxide at the interface compared to in the silicon at that interface. Okay, so this region of energy band bending, that's the depletion region. So that's the region where the semiconductor is depleted of majority carriers, that is holes in this case. So the surface becomes less p-type. Any questions? Oh, so just to be complete, what is this distance here? Very good. All right, 4.8 eV. Okay, any questions about the equilibrium, how to come up with an equilibrium energy band diagram for an MOS structure? I mean, just qualitatively. So in this lecture, we're just going to discuss qualitatively. And the next lecture will give you, derive formulas for exact depletion width, and the total amount of band bending in the silicon, and the total voltage dropped in the oxide. But qualitatively, does this make sense? Yes, Andrew. Good question. So the question Andrew asked was, okay, is there going to be band bending in the degenerately doped silicon? Actually, that is one of the non-idealities. So ideally, the polysilicon is doped so heavily that you will not get any kind of depletion or, you won't get any kind of depletion in the gate. But in practice, it actually is not easy to heavily dope the polycrystalline silicon down uniformly all the way down to the bottom interface. And this is actually true more so of p-type polysilicon because so usually the way this is done is that we deposit the polysilicon and then we implant it with dopants. We just shoot dopants into it and then we heat up the structure and allow atomic diffusion to take place. So the implanted dopants diffuse down to the oxide interface. But what happens, especially for p-type dopants, boron, the boron actually likes to be in the silicon dioxide more than in the silicon. And so that actually, then the boron can actually, some of it could end up going into this silicon down there and start changing the doping there. So that's undesirable. So for that reason, people are very careful not to get too much dopant right at the oxide interface. And so this metal gate is actually not super heavily doped right at the oxide interface. Anyway, so bottom line is, what would happen if the polysilicon, N-type polysilicon gate were not degenerately doped? So let me just draw. We're going to actually come back to this later, but let me use. Oh, you can't distinguish that. What color should I use? Maybe orange? Okay. If the silicon gate were not degenerately doped, you actually can also get some band bending. So remember, what is the width of the depletion region? How does it depend on the dopant concentration? Right. If you increase the dopant concentration, the width decreases. Right. So what we're kind of implicitly assuming is that this polysilicon gate is doped so heavily that any depletion that's happening there is really small, like negligible. But in reality, in some modern CMOS processes, it actually isn't necessarily so super heavily doped. So I'm going to exaggerate here. So the width of the depletion region might be significant compared to the oxide thickness. Okay, so what happens is then you'll have some band bending in the polycrystalline silicon gate as well. Okay. All right, so fundamentally, what does band bending represent? Like if you have a semiconductor, you're looking at an energy band diagram, and you see band bending occurring. What does that mean is happening in your semiconductor? Well, there's something changing. Okay, there's something changing with distance. So yes, there's some charge that's causing the band bending. But even more, okay, so what happens if you have some charge density? You have electric field. And what happens when you have electric field? Voltage drop. Very good. So if there's energy band bending, that means there's a voltage being dropped. Okay? So what this means is that, okay, as we apply a voltage here, where does that voltage appear? Well, part of it's going to be dropped across the oxide. Part of it's going to be dropped across the silicon in the, let's say, the depletion region. So part of it will be dropped across here, part there. And if you have this gate depletion effect, if that's significant, then that means you also have some voltage dropped within the gate. Okay? So you're applying, let's say, 1 volt, and ideally you'd like to have that voltage impact the conductivity of the silicon surface. I mean, this is how a transistor would work. You apply voltage to the gate, and you affect the potential of the electric potential of the semiconductor at the surface to turn on or off your transistor. Okay? So if you're actually wasting some voltage by dropping it across the silicon gate, then you're going to make your gate control less effective. So it just turns out that this gate depletion effect is not desirable. We don't want to waste any voltage drop across the gate, and actually not too much over the gate oxide as well. So that's why one reason why with transistor scaling, we try to scale the thickness of the oxide, because we want to have better and better control of the transistor channel region to turn on and off the transistor. As we scale the lateral dimensions, we have to scale the vertical dimensions as well. Okay. In any case, so ideally, very little voltage is dropped across the oxide, and and also across the gate itself. We would like to have most of the applied voltage ideally drop across the silicon. Okay, so this, I'm just going to label it now. This distance here represents, so this total amount of band bending in the oxide, that's the total voltage dropped across the oxide. And this total amount of band bending there, that's the total voltage dropped across the silicon. So that's Vs. Okay? So ideally, Vg is equal to V ox plus the voltage dropped, okay, across the silicon. Ideally. Okay, so now we're going to talk about flat band. There's actually a flat band voltage. Yeah, okay. So let's talk about flat band. So the flat band voltage is defined to be the voltage that you need to apply to get rid of the band bending within the semiconductor. Okay, so the flat band voltage is like a built-in potential. So for a p-n junction, when you bring the p and n regions together to reach equilibrium, there's going to be some built-in potential. So flat band is kind of a similar kind of concept. So let's draw the energy band diagram under flat band conditions. Okay, as I said, by definition, the energy band diagram in the silicon has to be flat. Okay, there's no energy band bending. So this is the flat band condition. So again, this is p-type silicon. This is silicon dioxide. Okay, so we know this is 3.1 eV, and this is 4.8 eV. Okay. And then for the gate, let's assume it's a N plus polysilicon gate. It's going to have the Fermi level at the conduction band edge, like this. Okay, so this is the flat band energy band diagram. Very easy to draw, right? Okay, so the key is it's defined to be flat band because there's no energy band bending in the silicon. And if there's no energy band bending in the silicon, that means the electric field is 0, right, at the edge here of with the gate oxide interface. And from the continuity of dielectric electric displacement, then that means the electric field must be 0 in the oxide as well. Okay, so it's flat. Okay, so that's the flat band energy diagram. So what is the difference? But there's a difference here between the Fermi levels in the silicon and in the metal, right? So what did I just say about if there's a difference in Fermi levels, what does that mean? That means something is being applied, right? A voltage is being applied. So this distance is going to be equal to it's going to be Q times the applied gate voltage. Now we have to figure out the polarity of the voltage. But let's just say quantitatively, okay, you should understand then if there's a difference in the level of the Fermi levels, so a difference in Fermi level in the gate versus the semiconductor, that difference is equal to the applied voltage. Okay? And this applied voltage, that's equal to the flat band voltage. Okay, so that's just a definition of the flat band voltage. It's the gate voltage you need to apply to get flat band condition. The applied bias voltage is equal to EF in the silicon minus EF in the gate. And to get the units right, you have to divide by Q. And that's defined to be the flat band voltage. Okay, let's think. In this case, is the flat band voltage positive or negative? I haven't thought about this recently, so why don't you, okay, why don't you take a minute, and I have to think about it too, so why don't you think about it, and okay, tell me if the flat band voltage is positive or negative. Let's go back. The work function of the metal is smaller than the work function of the semiconductor. Think of it as applying a voltage to the gate to raise the Fermi level up, right, to flatten the bands, right? We're raising the Fermi level on the left. If you raise the energy for electrons, that means you're making it more negative, the gate more negative. So the flat band voltage is actually phi m minus phi s, which in this particular example is negative. Okay? Now this is the ideal case. Next week we'll talk about non-idealities. The flat band voltage actually can be different if you have some charge in the oxide. Okay, so we'll talk about non-idealities like gate depletion, oxide charge. Those will change the flat band voltage a little bit. But ideally, if you don't have oxide charge, the flat band voltage is just different. Oh, got to divide by Q, right? The units. So flat band voltage is in volts, and the work functions are in units of electron volts. Okay, so yeah, to get the units right, you have to divide it out by Q. Okay, so remember, in the previous slide I had mentioned, okay, if you're applying a gate voltage, that gate voltage will be shared between the oxide. So part of it will be dropped across the oxide, part of it dropped across the silicon. But there's essentially a built-in voltage, the flat band voltage. They have to add to this as well. Okay? Okay, so forgot the terminology. We'll call this, sorry about that, we'll call that phi sub silicon, phi sub s. And yeah, because these are different in different textbooks. So phi sub s. So phi sub s is the total voltage dropped in the silicon, in the semiconductor. Phi sub f, which we introduced earlier, is the bulk potential. Okay, so it's different. So there's two phi's being introduced in this lecture. Okay. So this is an important equation that we're going to come back to probably during the next lecture and the one after that. Okay? So basically, you apply voltage externally in the circuit to the gate, and it's a voltage difference with the semiconductor. Internally in the device, that voltage is shared between the oxide and the silicon. Okay? Okay, so here's the definition. Well, it's kind of one definition of the total amount of voltage. The voltage drop in the silicon is just equal to the total band bending in the semiconductor. Right? So where is EI? Okay, let's go back. Exaggerating. The EI is basically located near mid-gap. So basically what this equation states is that, okay, what is the total amount of band bending in the semiconductor? That's just this distance here. Right, so this is the so-called the bulk region, and right here is the surface, at the gate oxide interface. Okay, so this distance here is Q phi sub s. Okay, that's all that this equation states. It's just, so the total amount of energy band bending in the silicon, that's going to indicate the total voltage dropped in the silicon. Okay? So when the applied gate voltage is equal to the flat band, then you have no voltage dropped in the silicon or in the oxide. Okay, so the final two slides we're going to go through a little slowly, because now, so now we know how to draw energy band diagrams, and an MOS capacitor, especially if we're using it as part of a transistor, we operate it over a range of voltages applied. So there's different regimes of operation. So you just have to remember three regimes. Well, okay, there's flat band, okay? And then there's three regimes of operation. There's accumulation, depletion, and inversion. So all of these terms are referring to the state of the semiconductor surface. Okay? accumulation means that the surface of the semiconductor has more majority carriers than the bulk of the semiconductor. So majority carriers are accumulating at the surface. Okay, so that's what it means. So in the case of a N-type silicon substrate, wait, did I have this wrong? Let's go to P-type. Okay, because we were talking about P-type, so let me go through this first. Do you have a question?
No, it was answered in the slide, but I was wondering if
Yeah, these are bullet points, sorry. Yeah, in the slides, I guess confusing. Okay, so let's continue looking at P-type silicon, and we'll end on N-type silicon. So this P-type silicon is relevant for NMOS, or N-channel MOS devices. Okay, so we reviewed flat band. Okay, on the very left here we have flat band condition. So on this chart, this is taken from the Perret textbook, we have the energy band diagram, and in the middle I indicate the gate voltage bias condition. And then at the very bottom we introduced the charge density plot, so the charge distribution. And then at the very bottom we indicate the condition, whether it's flat band or if the surface is accumulated or the surface is depleted, or if the surface is inverted to be the opposite type. Okay, so accumulation again refers to the fact that the surface has more majority carriers than the bulk. Depletion, by the name, hopefully it's obvious. The surface is depleted of the majority carriers. So there's a depletion region, okay, and the charge density there is just going to be minus QNA if it's a P-type semiconductor. And then if you, so the final range of gate voltages that can affect the surface, can cause the surface to go into inversion. In other words, the surface actually changes type. Okay, so in this case, rather than, you have P-type silicon in the bulk here, right here, right? The Fermi level is closer to the valence band edge than the conduction band edge, so it's P-type. But at the surface, the semiconductor has changed to be N-type. Okay, so we call that inversion. Yes, Ali? VT, oh yeah, okay, so there's a threshold. Okay, so that's what we're going to cover next time, because we have to give you an equation for that. A little bit arbitrary, but VT is called the threshold voltage, and that's the voltage that at which you actually start to form an inversion layer. So that's the gate voltage you need to apply to make the surface just as much N-type as the bulk is P-type. A little bit arbitrary, but basically, let's say let's say in this case, if the silicon were doped 10 to the 17, P-type, the surface would have 10 to the 17 per centimeter cube electron density. Right? So that's the definition of the threshold voltage. You just perfectly invert the surface to be of opposite type as the bulk. Question? What determines the thickness of the depletion region? That's a good question, and we're going to derive the equation for the depletion width next time. But very basically, the depletion region width, you remember from a p-n junction, it's going to be equal to, I might have a mistake here, but basically it's going to be, that's correct. I haven't looked ahead. But hopefully this looks kind of familiar to you. Right? The depletion width, we still will use a depletion approximation to derive this expression for the depletion width. But see, it's going to be, fundamentally, the reason why depletion width exists is because there's charge, or there's voltage dropped across the semiconductor. So here, the voltage dropped across the semiconductor is phi sub s. So remember in the past when we talked about a metal semiconductor contact or a p-n junction diode, we were looking at VBI minus the applied bias, right? That's the total band bending in the semiconductor. So here, the total amount of band bending is phi sub s. So basically, that's the equation for the depletion region width. It's basically the width to which you have to have this charge density in order to support the voltage drop that's being dropped in the semiconductor. Okay? Yes, Louis?